I think in the real world, in the wind farm, you would not expect to see any change. So let's see what they have to say about all these investigations there.
Okay, thank you.
Sorry, just 1 second.
On your Teams, did you switch the? So I just want to double check that you can be heard online here. Sorry. Okay, just double check. Yep. Okay, great.
Okay, thank you. So my name is Pavel Viochna. I'm from Icon, but I'm representing Škoda in this session. The presentation will be a little unusual because we have two presenters. That's because there are essentially two almost separate studies with slight overlap. We are concentrating on noise factors, so there will be no comparison to experiment and not even comparison to results-wise to each software. In Škoda, we rely heavily on transient simulation for many years, let's say. We use two softwares for that, iconCFD and STAR-CCM. And as was said before, it's crucial for us not only the accuracy, but also the precision. Because when there's some uncertainty in the difference of two cases, or in one case compared to the other, then if the uncertainty has the same order of magnitude as the difference itself, then in the development of cars, there's a risk of interpretation of the results. So this is very sensitive. That's why we are doing this. For both studies, use AutoCFD provided baseline grids, with some exceptions that my colleague will state explicitly. And okay, so the first part is in iconCFD. We've run 35 cases for each case, driver case, case A and case B. And we are focusing at first on the difference between those two. So we are not focusing in both the presentation, we are focusing only on drag for simplicity. And at first we are focusing on the difference between the two variants and not the difference itself, but its spread, let's say. Because as was already said, we run 35 cases with different viscosity, but the difference is in 5 decimal place. A different velocity inlet, different velocity at inlet, but also third decimal place, different number of cores. Each of those runs should be the same, but we know also from previous experience, because we did similar study on Škoda geometry itself, also on Škoda geometry. I will present the results later on. And this is not a surprise that actually there are differences. And if you look at the maximum and minimum difference of those cases, there is a spread of 3 counts, which is a lot compared to the difference itself. And especially because all of those 35 cases are average over 10 seconds, which is very long time. Also for each case, we simulated a 60-second simulation for reference. Okay, so why is that? If you look at the specific cases, not the difference itself, there's still a spread around 2 counts, the maximum and minimum value of drag, there's 2 count difference. And you can look at this to be a noise, essentially. That's because if you look at the error distribution, this is if you take the 10-second average value and you compare this to a reference value, which in this case it's the 60-second long simulation, but you can also use the average of all the 10-second cases. This doesn't make a difference. So you end up with this kind of distribution, which is more or less normal. So looks like this is stochastic behavior. And also, if you look at the sensitivity to different changes, it's almost the same, with the exception of number of cores, which looks like there is some correlation. But from what we know with the previous study on Škoda geometry, This is basically a coincidence because we have only 5 different core numbers. So this is just a statistical error from what we know. Okay, a little side note about initialization. As you can see, maybe from the flow field, roughly after half a second, you can't see the runs initialization anymore. So we are using runs for initializing, and then we flash the domain. We wait a little, in this case 3/4 of a second, and then we start averaging. So we wanted to make sure that this doesn't have any effect on the conclusion from this study. Obviously, after 10 seconds of averaging, you cannot see the difference if you flash the domain by 3/4 of a second or 2 seconds. You cannot see it in the flow field. So what we did was create a graph like this. It's average error relative to the reference value. It's average from all 35 cases for each case. And then you should see if there is some remnant of the run's initial solution. You can should have seen this in this error. The domain flashing is already cut away, so you start averaging, and then with cumulative averaging, the error is diminishing. And if there is some error, you should see it. And you can cut more from the beginning, and you don't see any change. And also, if you compare it to data, the same data backwards, then the error is still the same. The characteristic error over average time is the same. So the conclusion from this slide is that all that I will say on the next slide is valid regardless what amount of time to flash the domain is used. Okay, this would probably be the most important slide from my side. It's not something crazy. You're probably aware of it. With a larger averaging window, the error decreases, but it's nonlinear. At let's say first second, the decrease is rather sharp. But if you want very small uncertainty of the result, you actually have to average over a very long time. And even up to 10 seconds, there are some variants. The gray ones, there are still one count off or even more. That's the error compared to the reference, which means that the spread could be double that. Those are the 2 counts I already talked about. So this is a bad thing that you need to average over a longer time. Then the error gets, or the error band gets narrower, as you can see. And there's, I can tell you an example. For example, I want to know the effect of different number of cores. So I have some reference case. Then I simulate on different number of cores. And what is the most likely outcome that the error would be? 0. So let's say after 1 second of averaging, I have 0 difference compared to the reference simulation. So, okay, great. Then I conclude, well, there is no effect in number of cores. Then I have a different one. Let's investigate effect of different inlet velocity. But I could have some different value from those variables. Let's say this one. So I will end up with an error of 2 counts. So I will conclude, okay, there is significant effect of boundary conditions. Well, actually, both conclusions would be wrong because the effect for both is the same. Just have this spread. Most likely, the outcome will be 0. But if I do enough simulation, I can end up with 3 counts or even more, depending on my averaging window. And if I want to decrease it further than 1 count, let's say, I just need to simulate over larger time period. Okay, so that means that from a single simulation, I can say if there is an effect or not. That's the basic conclusion. But I can create average characteristics like this, like the green one, for example. But of course, this is very expensive. And the question is, does it depend on something? Can I change it? And that will be a topic for my colleague, but I can start with the sensitivity to different input. So if I have a different car, different input geometry, is the characteristic the same or not? Well, for the driver case, it is almost exactly the same. But we know from our previous study on Škoda geometry that it isn't the case every time. For, let's say, normal limousine-like car, Škoda, which is like the dark one, you can see that the characteristics is almost the same as in the driver case, which is also a limousine. But we have some cars, sometimes cars like hatchback cars or squareback cars has much larger error. You can see on the light green case. So yes, the conclusion is the characteristics of error based on average time. It is sensitive to input geometry, or it could be. And there's one last note. It's not in the. It's only a note. It's on the presentation, but because it would be a presentation in its own. Obviously, to obtain such a smooth curve, or less smooth, it's very expensive. So what we did in Škoda is we used experimental measurement data that we had because we had like 1,060-second long data signals from measurement, and we end up with very similar curves, even though the source of the noise is probably very different in measurement. Yet still the characteristics are very similar. And what's even more important is if you have a car that's behaving like this, it has a larger error. It's also true in the measurement data. You can see it. So now I will hand the word over to Marcus.
Okay, so we are presenting this as one presentation, but it was run very much independently. And my interest was a tiny bit different, but very much in the sense of the question that we already had. I wanted basically to know if there's some settings which can reduce the spread of the results that my colleague just described. So my approach was basically to create what I call data sets. Each data set is one setting, for example, shorter time step, longer time step. So each of these settings is subjected to all those noise factors that are listed in the table above. So each data set contains 15 or 17 runs. That depends on the mesh that I've used. You'll see on further slide. Yeah, so the data set looks like the column in step 1. What I'm going to be presenting here is the extracted envelope of those results. So finally, you will see plots like the one on the right, where there's the max-min development over time and compared for different settings. The base settings was in STAR-CCM using DDES, simplex solver. I'm not using grants initialization. I'm using long step DDES initialization. Then I discard the next 2 seconds, which are already at the final time step, averaging for the next 6 seconds. So I've been using 4 meshes, which was not really the purpose initially. I wanted to use 2, but yeah, whatever. It just happened. No, because it started before the mesh update from AutoCFD. So there are 2 meshes from AutoCFD, and with my mesh, with my custom mesh, which I wanted to make as close to the committee mesh as possible. I had occasional stability problems, and I also wanted to reflect on the changes that the committee mesh underwent. So yes, that's the STAR-V2 mesh detailed here. This might seem the details are actually so small. It was kind of challenging to really show them, and this might seem like out of place. Boring details, but you'll see 2 slides later why I'm really stressing these details out. So apart from some edit mesh refinement, according to AutoCFD 4 mesh, I've also improved some details in geometry. For example, the tire rim contact, which previously I had sealed by wrapping with just a very tight gap, and I went for a bit more robust over 1 millimeter sealing right in the geometry to have smoother surface without those artifacts, which hopefully some of you might see. Also, some changes to the exhaust bracket, because that was another source of stability problems. So let's go for the results. And first of all, the time step, as was already questioned. I've ran this for 3 different time steps. One conclusion is that you can already see that even after 6 seconds of averaging time, you will arrive at 2-3 counts difference for those 15 launches. So that's quite a lot, I would say. But yeah, it's very normal from our experience. But it's just uncomfortable, of course. We don't want that. But yeah, changing time step basically didn't help. Also, another message, which I think is rather interesting, is that changing to the updated mesh produced very much or very similar characteristics, which yeah, I'm kind of lost as to how to explain that, because that's really, I would say, remarkable. Because between the original and the updated mesh, it's not just the difference of some nodes. It's really a lot of edit refinement, particularly in the tire patch area. So yeah, interesting. I also tried to basically improve the convergence inside the time steps by raising inner iterations, by switching to double precision version of the software, and yeah, also reducing the convergence in pressure solver. Again, not really much of a difference. Maybe the convergence tolerance in the solver is slightly better, but I would say it's on the edge of statistical error. This is, as I said, these are the meshes, the custom meshes, and this is much more yeah, striking, I would say, because with my first mesh, I've arrived at much larger spread than using the committee mesh. You can see that for some of those, the spread is up to 5 counts after 6 seconds of averaging, and that's in the normal OEM world. That's nasty. That's like awful. And there also seems to be some effect of refining the mesh, which seems to even increase the problem. On the other hand, using Glow-Eye plus mesh seemed to improve the situation. Now, using the improved quality and improved refinement mesh, the STAR-V2 mesh, I've arrived at completely different conclusions. So even those tiny differences seem to really had a large effect. And yeah, also the particular conclusions about refinement inside the mesh or using Glow-Eye plus are yeah, completely different now. The improved quality led to much more stable results, not only in the spread that we are talking about, but also between each other for different refinement levels. And finally, I've also done this on different hardware environment, different clusters. Not really much to talk about here. It's basically all the same. And for the turbulence models, again, short story, I would say. The Volt model S seems to produce much more stable results. The error basically decreases much faster initially. So yeah, I think that's pretty interesting. Yeah, let's go on. This is the final slide. Having run these studies, we thought, okay, let's compare what we can. So we try to compare the situation at 6 seconds. Obviously, this is a different amount of runs for each solver and so on. So this is just a rough comparison, but yeah, even like that, we've arrived at very similar values for the error of drag. Yeah, different solver, different turbulence model, but the nature, basically, I would say, is very similar. Okay, conclusions. I would say the DrivAer model is suitable for studies like this because it exhibits very similar behavior to what we are seeing in our cars. But even though we would classify it as being on the stable side, we see much worse behaving cars. The error decreases non-linearly, as my colleague said, and doesn't really matter on the starting point of averaging and the noise sources. Again, doesn't really matter on tiny geometry differences. The behavior is very similar for case A and case B. We found out that there seem to be two major aspects that can influence the spread of results, and that is mesh quality and turbulence model. And on the other hand, much of the other options were neutral, including mesh refinement levels, hardware, and so on. So if this was a bit too complicated and so on, I would like to stress one thing to conclude. I would ask everybody to avoid judging fine differences from results average for less than 3 seconds, which unfortunately I've seen some of these in the last day. So yeah, thanks. That's it.